So take a look at this function here. One of the most important things, I hate to say most important, but a really important thing we can ask about a function is how fast is it changing? Is the temperature changing rapidly and we need to be concerned? Are our sales numbers increasing slowly and we need to be concerned? So how can we do this? How can we talk about the rate of change of a function? Well, I've got 2 points highlighted here for us to use this as examples, right? This point down here is 3, negative 12. And this point up here is 5, 30. And I've got the function over here that I actually use to graph this. So you can confirm for yourself if you like. Substitute 3 and 5 in there and confirm that those are the corresponding y values. So how am I going to define the average rate of change between these 2 points? Well, actually, I'm going to use something that you already know. We already have a way of describing the rate of change of something, right? Flashing back to earlier algebra classes. The rate of change of a line is the line's slope, right? So I'm going to define the average rate of change between 2 points to be the slope of the line connecting them. And this line actually has a special name. If you kind of flash back to your geometry classes, this is called a secant line, right? It's the line that crosses the graph at 2 points. All right, so now I can find the average rate of change easily enough. I'm going to abbreviate that ARC. The average rate of change is 30 minus 12. 30 minus, make sure I give them the right order, over 5 minus 3. That's 30 plus 12. That's 42 over 2, which is 21. A pretty big number by slope standards, and that seems to fit. That secant line that I drew there is pretty steep, right? The line is going up at a pretty sharp angle. So that number is consistent with what we're seeing on the graph. All right, so let's look at another example here. And what I want you to do, I've got 3 secant lines drawn here, and notice what I've done. I've kept this point down here constant. Then this is the line that we used on the previous slide, and then I drew 2 more. I picked a second x value that was a little closer to 3, and then I picked a third x value that was even closer. You notice what this line is doing? It's kind of pivoting on this point down here. And as it pivots lower and lower, as this second x value gets closer and closer to 3, this secant line is starting to look more and more like a tangent line, a line that only touches the graph at 1 point. All right, so what I want you to do, just for a little practice here, is calculate 3 average rates of change, right? Actually, you're going to calculate 2 because I already did 1. The average rate of change between 3 and 5, we calculated that already. It's 21. I want you to do the average rate of change between 3 and 4, and the average rate of change between 3 and 3.5. And I've given you both the x values and the f of x, the y values, right? So you can just use the values from the table, save you having to substitute numbers into that function, and figure out what those average rates of change are. Then we'll come back and discuss them. All right, so between 3 and 4, it's going to be 0 minus 12, 0 minus 12 over 4 minus 3, which is 12 over 1. That's just 12. And then for 3.5, it would be negative 7.875 minus 12 over 3.5 minus 3, and my calculator tells me that is 8.2. 0.25. Now, I want you to notice something here, because something interesting is happening. That denominator is getting closer and closer to 0. Right up here, I didn't rewrite the calculations, but here the denominator was 2. Here it's 1. Here it's just 0.5. Remember, we can't divide by 0, right? And what normally happens is the closer the denominator gets to 0, the bigger the quotient is. It kind of starts to blow up. But that doesn't seem to be happening here, right? In fact, not only is the number not blowing up and getting huge, it's getting smaller. Well, that's an interesting behavior, right? And this is something, I mean, this was just good practice for us here, but that's something I want you to kind of file away in the back of your mind, right? Because when you get to calculus, hopefully some of you will eventually take calculus here, you're going to talk about something called the instantaneous rate of change. The instantaneous rate of change is the slope of that tangent line that our secants are getting closer and closer to. And it turns out that despite the fact that the denominator is getting really close to 0 here, that ratio is actually going to settle down to a single number. And again, it's a calculus concept. I'm looking ahead a little bit, right? But you will be able to eventually answer that question, what is the slope of a tangent line? And that'll give you what's called the instantaneous rate of change. All right, so what's next? We're kind of done looking at properties of functions, right? And in the next lecture, we're going to continue talking about functions, but we're going to go in a different direction. We're going to talk about something called a piecewise function, which is a function that's defined using more than one formula, right? And you'll see this is useful in situations where the formula changes. For example, the example we're going to use, we're going to talk about payroll. When you make less than or equal to 40 hours, you get paid using one formula. Then when you cross over and you work more than 40 hours, you get paid using a second formula because it has to take overtime into account, right? Piecewise functions are a tool that we can use to describe that kind of situation.